Imagine two twins, both born on the very same day. They look alike, they sound alike, they share a birthday, but their futures will be very different. One twin decides to stay on our beautiful blue planet Earth. She will live her life here, watching the seasons change and the years go by. The other twin is an astronaut. He has a grand mission. He will board a powerful rocket, travel far out into space. He will journey at incredible speeds, exploring the vast emptiness between the stars. It seems like a simple story, a tale of two paths. Years pass on Earth. The twin who stayed behind grows older. She celebrates many birthdays. She sees the world change around her. She waits for her brother to return from his long journey. Finally, the day comes. The spaceship lands back on Earth, a shining metal teardrop returning from the cosmos. The astronaut twin steps out. But something is astonishing. Something is truly mind-blowing. He looks younger than his sister. Many years have passed for her on Earth. Only a few years have passed for him in his spaceship. This isn't science fiction, this is a real effect of our universe. This strange and wonderful idea is at the heart of Albert Einstein's theory of relativity. It tells us that time is not a constant universal clock that ticks the same for everyone, everywhere. Time is relative, it can be stretched and squeezed. It can flow at different rates for different people. The rate at which your personal clock ticks depends on two things: how fast you are moving, how strong the pull of gravity is around you. For the spacefaring twin, his incredible speed through the cosmos literally slowed down his time compared to his sister on Earth. He aged less because he traveled more. So, how is this possible? It feels like it goes against everything we experience in our daily lives. Our clocks all seem to tick in perfect harmony. But that is only because we all live on the same planet and move at relatively slow speeds compared to the speed of light. The universe, however, operates on a much grander scale. It follows rules that are often hidden from our everyday view. To understand this cosmic secret, we must change how we think about time itself. We have to see it not as a rigid ruler but as a flowing river, a river that can speed up and slow down on its journey through the cosmos. For most of human history, we thought of time as something simple. It moved at the same speed for everyone and everything in the universe. This is the world Isaac Newton described, a world with a single master clock for the entire cosmos. But Einstein suggested that time is not separate from space. Instead, they are woven together into a single four-dimensional fabric. He called this fabric space-time. Think of it like a giant stretchy sheet of rubber. This was a revolutionary idea. It meant that time wasn't just a background measurement, it was part of the very structure of the universe itself. Einstein's theory of special relativity stated that the speed of light is the ultimate speed limit in the universe. Nothing can travel faster, and crucially the speed of light is the same for everyone, no matter how fast they are moving. This simple fact has enormous consequences. It means that something else has to change to keep the laws of physics consistent for everyone. That something is time. Time itself must slow down or speed up to ensure the speed of light remains constant for all observers. This slowing of time is what we call time dilation. Dilation just means to stretch, or expand. So, time dilation means that time itself is being stretched out for an object that is moving very fast. A clock in motion will tick slower than a stationary clock. It is not a trick. It is not a mechanical error with the clock. The clock is working perfectly. It is the actual flow of time that has changed for that moving object. This idea completely changed our understanding of the universe, turning Newton's simple river of time into a dynamic, flexible, and utterly fascinating cosmic ocean. Let's dive deeper into this idea of speed affecting time. Einstein's special theory of relativity tells us that the faster you move through space, the slower you move through time. It's a fundamental trade-off built into the fabric of space-time. You can use your motion to travel through space, but then your progress through time slows down. In daily life, the change is incredibly small, a few nanoseconds at most, far too tiny to notice. To see a really dramatic effect, you need to travel at speeds that are a significant fraction of the speed of light, about 300,000 kilometers per second. At 99% of light speed, every year for you is more than 7 years on Earth. At 99.9%, 1 year is nearly 22 on Earth. You'd effectively travel into the future. This is the twin paradox. The astronaut twin's biological processes, his thoughts, his heartbeat, everything slows relative to Earth. It is not that he feels like he is in slow motion. For him, time feels perfectly normal. A minute is still a minute. But when he returns and compares his clock and his age with his twin on Earth, the difference becomes real and measurable. Speed is a key that can unlock a different flow of time. Speed is not the only thing that can bend and stretch time. Gravity can do it too. This was Einstein's next great idea. The theory of general relativity, published in 1915. He realized that gravity is not a mysterious force pulling objects together, as Newton had thought. Instead, gravity is curvature in space-time. Massive objects, planets and stars, create a dent in this cosmic fabric, much like a heavy bowling ball on a stretchy sheet. Planets don't orbit because of a pull, they follow curved paths carved by mass, rolling along gravity wells. This warping of space-time affects time itself. Time runs slower in stronger gravitational fields. The deeper you are in a gravity well, the slower your clock will tick. On Earth, people at the surface experience time slightly slower than someone in higher orbit. Your head ages slightly faster than your feet, a real but minuscule effect. Near a black hole, time could slow to a crawl. While you might experience only a few hours, billions of years could pass for everyone else. Gravity's grip on space-time is powerful. It holds galaxies together and dictates the pace of time across the cosmos. We don't need to travel near the speed of light to see time dilation in action. Actually, we can see it right now, with astronauts orbiting our planet. The International Space Station, or ISS, orbits Earth at about 7.66 kilometers per second. This incredible velocity means astronauts experience special relativity. Their high speed causes their time to slow down compared to us on the ground. It's the speed effect. It's real and measurable for everyone who goes into orbit. But there's another effect. The ISS orbits about 400 kilometers up. At that altitude, gravity is slightly weaker than on the ground. General relativity says weaker gravity makes time run faster for the astronauts. So we have two competing effects. Their high speed slows their time down, while weaker gravity speeds their time up. Which one wins? For the ISS, speed wins. The astronauts' velocity is the dominant factor, so they age more slowly than people on Earth, but only by a very tiny amount. Every 6 months on board, they age about 0.005 seconds less. Not enough to stay young forever, but concrete proof that tiny future time travel is possible. When astronauts like Scott Kelly spend a full year in space, those fractions add up. After his year-long mission, he was slightly younger than his identical twin, Mark Kelly, who stayed on Earth. The twin study let scientists study spaceflight effects on the body, and it was a real-life example of the twin paradox. Scott Kelly became a very slight time traveler. He returned to an Earth a few milliseconds older than he was. Long before we had astronauts living on a space station, scientists wanted to test Einstein's theories right here on Earth. In 1971, two physicists, Joseph Haffel and Richard Keating, designed a simple experiment to do just that. They used the most accurate clocks available, atomic clocks. The plan was straightforward. They took 4 atomic clocks and put them on commercial airplanes. They flew the clocks around the world, twice. First eastward, same direction as Earth's rotation, then westward, against it. Both flights were at high altitude, where gravity is weaker, which makes time speed up due to general relativity. When the planes landed and clocks were compared, results matched Einstein. Eastward clocks lost about 59 nanoseconds, westward clocks gained about 273. The first direct empirical evidence of time dilation. You might think that time dilation is something that only concerns physicists and astronauts, but you probably use technology that relies on correcting for time dilation every single day. If you have ever used a GPS on your phone or in your car to find your way, you have benefited directly from Einstein's theories of relativity. The Global Positioning System is a network of satellites orbiting the Earth. The GPS network consists of about 31 satellites at around 20,200 kilometers. Each satellite carries a very precise atomic clock. Your GPS measures signals from at least 4 satellites. By calculating how long the signals take to travel, the system triangulates your exact position. That requires timing accurate to a few nanoseconds. Just like ISS, GPS satellites face two competing effects. First, they're moving very fast, about 14,000 kilometers per hour, making their clocks run slower than ground clocks by about 7 microseconds every day, 7,000 nanoseconds. Second, higher altitude means weaker gravity. General relativity makes their clocks run faster by about 45 microseconds per day, 45,000 nanoseconds. Combined, the satellite's clocks run faster than Earth clocks by about 38 microseconds every day. That tiny offset would break GPS if uncorrected. Timing errors would build to roughly 10 kilometers per day. Within minutes, your phone could say you're blocks away. So next time you use GPS, remember, you're relying on one of physics' deepest insights. The mind-bending nature of time dilation has made it a favorite subject for storytellers. These stories take the real science of Einstein and push it to dramatic, emotional extremes. They let us explore the human consequences of time moving at different speeds. Perhaps one of the most famous examples is Interstellar. A team travels through a wormhole to a planet orbiting a supermassive black hole called Gargantua. The planet sits deep in the black hole's gravitational well, so time there runs incredibly slowly. 1 hour there equals 7 years for everyone else. Returning after a few hours, the crew find a crewmate aged by decades. It turns general relativity into very personal drama. Time dilation shows up in many other sci-fi stories. In Doctor Who, the Time Lord travels space and time in the TARDIS. The show often ignores strict physics, but the idea of stepping out of normal time is central. It explores loneliness and wonder for beings who see time as a landscape. From epic films to classic television, these stories tap a deep fascination with time. Exaggerated for drama, they still rest on real science. They remind us the universe can break the steady tick of a clock. From the simple tale of two twins to the complex engineering of GPS, the journey to understand time dilation reveals a fundamental truth about our universe. Time is not the rigid, unyielding metronome we once thought it was. It is a flexible, dynamic, and personal quantity. Every object, every person, every planet, every star experiences its own unique flow of time, dictated by its motion and the gravity of its surroundings. The universe is not governed by one master clock but by an infinite chorus of individual clocks, all ticking at their own rates. This realization is both humbling and inspiring. It connects us directly to the grand workings of the cosmos. The same laws that govern the spin of galaxies and the collapse of stars are also at play in the tiny, imperceptible slowing of an astronaut's watch. The principles of relativity are not just abstract equations on a blackboard. They are woven into the fabric of our reality. They are present in the light from a distant star, the signal to our phone,